This is lecture number 9 of the course ME314 Fluid Mechanics 2 and the lecture number 3 of this week. In the previous lectures, we have derived Reynolds transport theorem, and then we derived the equation of continuity using the Reynolds transport theorem. In the same connection, today we will derive a linear momentum equation using the Reynolds transport theorem. Okay, first go through the content. In today's lecture, we will first talk about the Reynolds transport theorem, and then we will derive a momentum equation using the Reynolds transport theorem. And this resulting equation would have three different terms. The term which is actually talking about the forces that are acting on a control volume we will discuss, and then we will go to the momentum accumulation term, and then the momentum flow term through the control volume. Let's see, you already know that this is something, you have a control volume of arbitrary shape. This is a differential volume, and the boundaries of the control volumes are actually called as control surfaces. So you know the left hand side is actually an Lagrangian part, so which talks about B is in any extensive quantity, or we call it a system, because this quantity of that system is being controlled, is not going to change in this Lagrangian description. So this term is representing the rate of change of that extensive quantity that has been taking place within this system. The right hand side we have two terms, both are actually representing this Eulerian description, because this is a fixed region of interest, what you call it a control volume. So some changes takes place within the control volume, we call it an accumulation term, plus there is some net flux taking place through the control surface. So the change that has been taking place in the system is actually depending upon how fast things changes within the control volume, plus something is coming out and something is leaving. Here V is a velocity vector which is measured relative to the control volume, and for simplicity in the beginning we will assume it that we have a fixed control volume. So I have explained it earlier too, so you must understand each and every term of the Reynolds transport theorem. And small b, we know that small b is its corresponding intensive quantity. So this extensive quantity B divided by the mass would result into a small b. So that would be an intensive quantity. And you know V dot n is a velocity component that is actually in the normal direction. So once some fluid is coming out, you see the velocity is a vector having two components. One is a normal component. So from this area, whatever coming out is only from the normal component. There is a tangential component of the velocity which always remains within the control volume. It doesn't cross the control surface. So that's why we always talk about a normal component of the velocity, and V dot n is nothing, just a normal component of the velocity. Okay, let's explore here. Today we are going to derive linear momentum equation. So our extensive quantity is B is a momentum. So in continuity equation our extensive quantity was mass, but here it is a momentum. So I can easily write over B, because B is a vector, because even mass is a scalar but velocity is a vector. So momentum is a vector quantity. We can easily put an arrow here too, because it's an extensive quantity. So how to work out its corresponding intensive quantity? Because you know the extensive quantity divided by the mass, you are going to get its corresponding intensive quantity, which is independent of mass. So here B is mass times velocity vector. So divided by the mass and mass cancels out. So the small b here is a vector as well. So both capital B and small b here are actually vectors. Small b is a velocity vector, capital B is a momentum vector. Okay, what we need now is, because we have expression for Reynolds transport theorem, so what we need is just substitute b here on the left hand side, capital B on the left hand side, and small b on the right hand side of this Reynolds transport theorem. So that would result into, because this capital B is momentum, so mass times velocity, I have put it here on the left hand side, and instead of B I have just substituted velocity vector, and with the small b I have just substituted velocity vector, so the rest remains the same. So the left hand side is representing how fast the momentum of a system is changing, and this right hand side is obviously talking about the rate of change of momentum that takes place within the control volume, plus the momentum flux takes place across the control volume through a control surface. So if we look it closely, we must know what each term is all about. So this term is about the rate of change of linear, because this product of mass and velocity is a linear momentum. We'll talk about later about angular momentum as well. So far today we will discuss only linear momentum. So rate of change of linear momentum of the system would be represented by this left hand side of this equation, Reynolds transport theorem. Once we substitute small b and capital B in Reynolds transport theorem, you end up with an expression. So that would result into a momentum equation, because the left hand side is a vector, so actually is a vector equation. This is the rate of change of the linear momentum that is taking place within this control volume. So this thing is mass per unit volume. Volume and volume cancels out, so mass multiplied by velocity would be momentum. So this is a momentum of a differential volume. So if you integrate it over the whole control volume, it is the momentum that has been accumulated within the control volume. And once you differentiate with respect to time, so you are interested in the rate of the momentum that has been linear momentum that has been changing within this control volume. And this would be the momentum flux term. So whatever the momentum crosses the control volume through a control surface, so that would be something called as a momentum flow term. So what is momentum going out minus the momentum going in? So this we will talk in detail today. So this equation, what we can do on the left hand side, so as you know, here the v is a velocity vector, and the velocity vector means it has components u, v and w. So these are the components of the velocity vector. This equation is a vector equation, so it has components in x, y and z, because velocity has a component in x, y, u, v and w are the component of the velocities in x, y and z. We know from the principle of conservation of linear momentum that according to Newton's second law of motion, we know that the rate of change of momentum is representing actually the resultant of the forces that is actually acting onto the system. And obviously this Newton's second law we are going to apply for inertial coordinate system. Inertial coordinate system means our coordinate system x, y and z is we are actually representing all the term through that coordinate system. And but this coordinate system is non-accelerating. It means either the coordinate system is stationary or moving with a constant speed. So if such a case, then it would be called as inertial coordinate system. So our Newton's second law of motion is applicable to the inertial coordinate system. So resulting equation would be, the left hand side would be nothing, just the sum of the forces that is actually acting onto the system. So the left hand side is about system. So we are talking about the entity that is present with in the region of interest. So this would be the forces resultant of the forces, not the applied force, but the resultant of the forces. When we derive the Navier-Stokes equation, I have already explained you the Newton's second law of motion quite in detail. So if you're not able to understand this equation, you can go back to that lecture too. So what we end up with, the left hand side is using the Newton's second law of motion is replaced with the sum of the forces that are actually acting onto the system. So this equation is called as the momentum equation in integral form, and how we have derived by just employing the Reynolds transport theorem to an extensive quantity momentum, and by using the Newton's second law of motion, the left hand side is actually representing the sum of the forces which are acting onto the system. So whatever those forces are acting actually to the external to this system, the region of interest, what you call it, a control volume. So right hand side represents as we already have learned, this right hand side represents the Eulerian description, or actually what is happening within the control volume. So whatever the changes takes place in the system is the resultant forces that has been taking place is depending upon the momentum change within the control volume plus the momentum flux through the control volume across the control surface. So this equation would be our central equation for today's discussion, and we will explore each and every term, what this term is all about, what this term is all about, and what this term is all about quite in detail today. And we know here the velocity is a vector, so this equation is a vector equation. It means the forces, the resultant forces that is acting onto the system would be for x direction, it would be the resultant forces in x, and in the y direction the resultant forces would be y, and the resultant forces in the z direction would be the so actually this is not a one equation. Actually for each direction x, y and z, we end up with three different equations, and we will see its formulation in the next slide probably. Okay, so the concept of resultant forces is very important, and I emphasized when I derived the Navier-Stokes equation earlier. The resultant force is actually the net force that is acting onto the system, and if the system is accelerating, so it accelerates on the basis of the net force that is acting. It doesn't accelerate on the force you apply. The acceleration is always due to the net force. Okay, let's say if you take an airplane, example of an airplane which is flying in a straight line and a level flight. So it means there is no acceleration. So what is actually happen is there are different type of forces. So the weight of the aeroplane acts downward. Let's say the lift force. So if the magnitude of the lift force is same as the weight, so these two vertical forces balances out. Okay, so your engine of an airplane produces a thrust, so that propels the aircraft in the forward direction, and there is an opposing force through the thrust, what you call it a drag force. So if these two forces are balanced, so the resultant force would be 0. So there would be no resultant force acting either in the horizontal direction or either in the vertical direction. So we call this to be a condition of mechanical equilibrium if we just consider the forces, not the moments that is actually acting in each direction. Okay, the idea is the resultant force is actually responsible for acceleration. Okay, look at more closely this aeroplane case. So let's say if your aeroplane is circling around something, so what we are doing is we are viewing this aeroplane from the top. So obviously once there is a force, what you call it, a centripetal force. So that is the force, and force is mass times acceleration. So there is an acceleration which is in the normal direction, which is keeping this aeroplane into this circular trajectory. If we look at the front view of the same, let's say if this is the case, the aircraft, the weight is acting downward, and the lift force is in this direction, making an angle theta to the vertical. So if I have vertical is in this x direction, so obviously once it is circling, there is a net force that is actually acting, which is responsible for this centripetal acceleration. So this net force is actually the resultant of these two forces. So once you vectorically add this lift force and the weight force, you will be able to get this resultant force that is responsible for an aircraft to circle. And we can represent it like this, because the lift force is in this direction, so just I brought it, this free vector, from this place to this place, and as we know the weight is always acting downward, so this vector plus this vector would be this vector. This is the resultant vector, or sum of the forces that is actually acting onto this airplane, which is responsible for this circling or providing motion of an aircraft in the circle. So this is actually the resultant of the force, sum of the resultant forces that is actually acting on an airplane. So whenever it is accelerating, because it is accelerating this acceleration is a centripetal acceleration, so this net force is responsible for this centripetal motion of an aircraft in circle. So the resultant force is always responsible for an acceleration. This is what we have learned it in simple case as well earlier. But if you look at here, if two types of the forces, the weight and the lift, then the resultant would be the responsible for its motion. Motion in a circle rather. Okay, let's see this our conservation equation in integral form more closely. If you look at here, so the sum of forces acting on a system, if you write it for x direction, so what I do here is here velocity component in x direction is u. So I am using a Cartesian coordinate system. So this is the sum of forces that is acting in the x direction of the coordinate system, and similarly here v is replaced with the velocity component, and you know this v dot n is actually a normal vector to this area, so it would be the normal component of the velocity in the direction normal to this area, so it remains like the same. Similarly, as you know that velocity is a vector, so this component of the velocity itself would be a function of space and time, because velocity is a vector. So this vector is depending on this information about its location and time. So this velocity vector, the component of the velocity itself is also a vector in x direction. Similarly, we can write for some of the forces that has been acting in the y direction as well as in the z direction. So what I have done is just replace v, small v, the velocity vector in the y direction. So I need to put the sum of the resultant forces in the y direction. Similarly, the velocity component in z direction is w here, so I have just put w here, the rest remains the same. So actually this equation is a linear momentum equation, and it is in the vector form, so it has its components in a given coordinate system. If we want to write it for one-dimensional case, we can write it like this. So whatever the force is acting in a one-dimensional case, in the previous lecture I have already explained the concept of one-dimensional flow. where the flow is in a dominant direction. So we are not bothered about, we are only bothered about the bulk velocities at the given cross section. So this V bar is, think of average or the bulk velocity at those different sections in the stream-wise direction. So this would be the sum of the forces, the resultant of the forces that are acting in the stream-wise direction, equal to whatever the momentum change takes place within the control volume plus the momentum out minus the momentum in. I explained you that this net flux term is a B out minus B in terms. So here we have so how do you see that why I have come across with the mass flow rate? Because you know from your continuity equation, mass flow rate is rho times u times area. So rho u area would be the mass flow rate, and this would be the component of the velocity that is coming out through a surface. So whatever the surface is. So this would be the right hand, this side of the equation can be represented like this too. So it is a much simpler form because we are talking about only the one-dimensional case. So the area term has been bunched together into this mass flow term, because mass flow rate is rho times area times the velocity. So this is more meaningful and more practical expression of this momentum equation, because most of the time we are dealing with the one-dimensional case. Or we will be dealing with the forces in x and y most of the time, not in the vector form. We are dealing in the, most of the time we are dealing in the algebraic form rather than a vector form. Okay, so we have momentum equation, linear momentum equation. This is in the vector form. So this is actually not a single equation but three equations. So you have forces in x, forces in y, and forces in z. Similarly, you have velocities in x, velocities in y, and velocity in z. The simpler form of the same equation, if you write it for a one-dimensional case, you can write like this. So this is something more useful, and we can see it in a map like this. This vector form is whatever the forces acting onto the system. So obviously acting on the system would be some external forces, and these are the momentum changes that takes place within this control volume. Plus this term is representing the net flux of momentum, flow of momentum through a control volume across the control surface. So this is this equation, and we can write in a simpler notation, simpler form for one-dimensional case like this. So here, since this expression is turned into from partial to ordinary differential, because we are only dealing with the one-dimensional case. So it would be just density is mass times density is mass per unit volume. So if I have to write mass per unit volume, volume and volume cancel out, so it would be mass times velocity. So that is what I have written here, is a mass times velocity. And here also it is actually the same expression. Instead of in this vector form, we can write in a simpler notation. So this would be the momentum flow out minus the momentum flow in. So all these terms we are going to understand in the later part of this lecture more closely. So this term is actually the net force term. So we have come across with three terms, and this term is what you call it an accumulation term. So what is the momentum change that takes place within this control volume, plus the momentum that has been transported through the control volume going out and going in. Obviously this going out and going in takes place at the surface, so that would be called as momentum flow. So in the next part we will talk about each and every term quite in detail. So let's start with the sum of the forces that is actually acting on the system. So we are talking about only the first left hand side of this momentum equation. So just take an example. We have a control volume, and x1, x2, x3, x4 are different forces that are acting in different directions. What we can do is we take the resultant, and if we just see that the sum of the forces in x to be worked out, or the sum of the forces in y to be worked out. So what we see here is, if we just see the x direction forces, so x2 and x3 is in the positive x direction, and x4 is in the negative x direction, which is x4 cos 30 component. So these two, which is positive, and these two would be negative. This would be the resultant force that is acting on this control volume. And if we see this control volume, so the horizontal force would be y1. If you see, and if it is going out, so it has x direction is y2 times cos of 30. Yeah. So that is something leaving out. That is something which is leaving out. So what we need to do is the left hand side is the forces. Left hand side is the forces. Right hand side is, we will talk about later too, because it's actually the momentum flow. So for example, in this particular problem, water is coming into this section and this way. So this is actually a force diagram. We will talk about it later. So right now just think of actually these x1, x2 are the forces, and y1 and y2 are actually the momentums. So what is momentum going out? Out is in x direction, y2 times cos of theta is the momentum out, minus the momentum in. Y1 is the momentum coming in. So this is a force diagram, this is a momentum diagram. We will talk later explicitly about this force and momentum. So right now we are just focusing on the forces, because we are only bothered about the left hand side of the term, the sum of that force is actually acting. And later we will learn, either we represent a force or momentum. Actually this is just a visual representation of this mathematical formulation. So these x1, x2, x3 are the forces, and the force balance is represented by the left hand side in x direction. Similarly, the force balance in the y direction would be x1 is the force in the y direction, and x4 sine 30 is the force in the y direction. So y is a momentum, so momentum out would be negative momentum out, and there is no momentum in the y direction, so that way it would be 0 minus something. So momentum out would be minus y2 times sine of 30, and momentum minus momentum in is 0. So right now forget about this momentum term, which is I have used letter y to represent momentum here, and x1, x2, x3 are x4 are the force terms. So for example, on the left hand side, the forces that has been acting onto the system would be depending upon the direction of the forces in x and the direction of the forces in y, which I have used this term for forces. So actually I must not write it here because I haven't explained momentum diagram yet. So it is just a force balance. Now we will talk about it later too. Then the next term in our momentum equation is the accumulation term. So now we have to understand what actually this term is all about. This momentum, take an example of a pipe band held by a flange. So we have water coming in from this place, and the dashed lines have been representing the control volume. So if I am interested in this small volume, I call it delta V. Delta V is the small volume. So if I am interested in calculating what is the momentum inside this control volume, so I have the mass that is present, that is the velocity, that would be the momentum. If I take the sum, it will be the momentum within this control volume. So mass is density times volume, so density times volume, and the velocity vector. So this thing can be written in this manner as well, because if you integrate it over the whole differential volume, this is a differential volume, if you integrated it over the whole control volume, you are going to get this expression rho times v times dv. So this is actually the same thing. What it represents is actually the momentum that is being within this control volume, and momentum is nothing, just mass times velocity, and mass is density times volume, and here I have just used the letter v, small v, to represent the velocity. So momentum inside this control volume is represented by this term. So this is the term. In the right hand side, what I have done is differentiated with respect to time. So now I am interested in momentum accumulation. Momentum accumulation is nothing, whatever the momentum within this control volume, how fast is changed with the passage of time. So rate of change of the total momentum, because once you have integrated, it will be the total momentum. So rate of change of total momentum within the control volume is represented by this term. So this term is nothing, just the rate of change of momentum that takes place within this control volume. So this we call it an momentum accumulation. Okay, and now move to the momentum flow term, because we have already talked about some of the forces, we have talked about this term, the momentum accumulation term, and the next thing is to talk about momentum flow. So this term is a more important term and more critical. So for simplicity, what I do is just consider a flow in a cylinder. So flow is taking place in a cylinder. So this is the center line of the cylinder, and just think of a particle which is crossing certain surface. So this particle, I have taken a very small size cylinder. So its area would be delta A, whatever the area is for this particle is here. Delta A is small area, and how much is the length would be, there is certain velocity to which the particle is crossing that surface. So the velocity is v, and the time it takes is, let's say, delta t. So the length would be meter per second multiplied by seconds, it would be meters. So this length would be v times delta t. So if I am interested in the volume of this particle, small volume, so this is small volume is the length multiplied by the this area. So here the length is v times delta t times delta area. So this is actually the small volume of this particle of the fluid which is crossing that surface. Let's say I'm interested in momentum of this one particle, just focusing on this one particle. For simplicity, I make it a bigger size so that I can appreciate that it's at certain volume, certain areas. So its momentum would be the mass of that particle times the velocity of that particle. As I know, mass is density times volume, and as I know, the volume is this whole length times area, and this length and area. So if this length is velocity times the time elapsed, delta t, so this would be the length, density, and this would be the area. So this equation is representing the momentum of one of the particle that has been crossing the surface. So there are so many particles crossing that surface. So what I need is to take the sum of all the momentum of all the particles. So if I take the momentum of all the particles, I have to take the sum of all the momentums of each and every particle. If I take the sum, I will get the momentum of all the particles. Then since there is a time term, so if because here it is differentiated with respect to time, here the momentum differentiated with respect to time, so here also something to be differentiated with respect to time. So if I take it a per unit time, so I get rid of this delta t, I only end up with rho v a change in area. So as you know that rho is the same here, and v to this area would be actually the normal component of the velocity. Yeah. And so I can write like this too. So this term is actually representing the momentum of all the particles per unit of time that is crossing through the surface. So that is actually the momentum that has been crossing, and obviously for simplicity I have just taken a one of the surface, but as we know this v dot n is actually representing the out as well as the in. In deriving momentum equation I have explained the physical meaning of this term quite in detail. So this is actually the momentum of all the particles that has been crossing per unit of time. So at this point of time we know that this is sum of the forces, this is an accumulation term, whatever the momentum change takes place within this control volume, and this is actually the momentum flow through the control volume across the control surface. So this is something, the momentum flow term. Okay, so take another example for understanding the momentum flow. Let's say we have a fluid, the jet, obviously coming through certain nozzle. So there is a jet of the fluid, and it is striking a vein. So this is striking a vein. So first thing to analyze this, because there is a fluid and there is a solid. So there is a fluid solid interaction, and at this section the fluid enters with velocity 8 meter per second, and its mass flow rate is 2 kilograms per second. This vein is having certain band, so that the fluid leaves at section 2 at an angle of 45 to the horizontal. Here the velocity once again the same as what is at section 1. So velocity is 8 meter per second. So its mass flow rate would be 2 kilograms per second. The same mass flow rate, same velocity at section 1 and section 2. So you know what is the momentum? Magnitude of the momentum flow would be the mass flow rate times the velocity. As we know, mass flow rate is rho times the volume, actually rho times the volume flow rate, actually volume flow rate. A times V would be the volume flow rate, because we are talking about mass flow rate. Rho A, rho Q. Mass flow rate is rho times Q. Q is a volume flow rate. And if you multiply by this velocity v, so you end up with v, and v would be, so this is we're not talking about the momentum, we are talking about the magnitude of momentum. So we are not bothered with the direction. So that's why it is rho av square is actually representing the magnitude of the momentum flow. Okay, now let's see if I am interested in calculating the magnitude of the momentum flow for this example. So my mass flow rate is 2 and my velocity is 8 meter per second. So kilograms meter per second is square, kilogram is mass, meter per second is square is acceleration, mass times acceleration is force, that is in Newton. So that would be the magnitude of the momentum flow. So if I have to write down the momentum flow, as I know the momentum is a vector. So I must have to represent mass is a scalar, but velocity is a vector. So here the velocity at section 1 is this is x direction, so I call it 8I. 8 is a magnitude, I is it's representing its direction. So that would be the 8I would be the magnitude of that. This is a vector in x direction at section 1. So the magnitude remains 16. 16I would be a vector. That would be a momentum flow at section 1. So if you see a momentum flow at section 2, so at section 2 what happens is This would be your mass flow rate, but here your velocity vector in this direction has component in x and component in y. Component in x would be 8 times cos of 45, and in minus y would be 8 times of sine of 45. So the unit vector j represents the y direction, because minus is here because it is downward. So you have this momentum flow at section 2. So keep in mind the mass flow remains same, velocity as a magnitude remains same. But since momentum is a vector, even though the magnitude doesn't change, magnitude remains 16 Newton from section 1 and section 2, but since the direction is changing, so the momentum at 2 would be different. So if I am interested in momentum change between 1 and 2, it would be subtracting momentums. So I have momentum at 2 and momentum at 1. So there would be a net momentum acting. So keep in mind here it is momentum flow takes place because there is a mass, there is a velocity, so there is a momentum associated, and since the mass flow rate is there, so it means mass is not stationary, it is flowing. So momentum in and momentum out is taking place, and the difference is the net momentum flow. And since because of the vector nature of momentum, due to the fact that velocity is a vector, so you have some momentum change even though the magnitude remains the same. So that is very important in this net flow term, because momentum is a vector. Okay, for this obviously once you are dealing with the forces, you always have to draw a force diagram. So force diagram is nothing. For example, case of a water flowing in a pipe band, there is a flange which is holding the pipe band. So the weight of the water and the weight of the pipe and the flange is represented by a resultant vector W, which is acting downward. So pressure which is forcing the fluid to come into this band is pressure vector, which is force is pressure times area. So it's a force vector in the due to the pressure. And you see Fx and Fy are actually the forces that has been acting on this flange, which is actually holding the this band. So let's say if there is no force here, so if there is a jet of water comes to the band, it will throw the band as the water is striking the band. Once it is not throwing because it is being supported by the flange, so flange is bearing the forces, and these forces are Fx and Fy. So force diagram is nothing, just a illustration where you have forces that is acting inside the control volume. Second is obviously this is somewhat similar with the free body diagrams in mechanics. So in mechanics you are dealing with the particles, so you are focusing on a Lagrangian approach, whereas in fluid mechanics we are dealing with the control volume. So that's why we use instead of saying it a free body diagram, we have given another name, what we call it a force diagram. Okay, another thing, as you see some mass is coming in and some mass is leaving. So there is at the same time some momentum is coming in, some momentum is leaving. So such diagrams are called momentum diagrams. Diagrams. So momentum in is this, momentum out is this. So we call it a momentum diagram, which is just an illustration for momentum. If we have a steady state problem, obviously there is no momentum that has been accumulated within the control volume if it is a steady state case. So in our equation, if you look back our equation, so this term would be 0 if it is a steady state case. So there is no accumulation of momentum, only momentum flow is taking place. If you see the same example once again, both the force diagram and the momentum diagram. So actually now we apply this equation to this particular problem, where pressure force is there, weight of the weight is acting downward, and this is the force in x and y that is being held by the flange. So if you balance the forces in x direction, so forces in x direction would be only Fx. There is no force in other than Fx. So this would be the force that is actually acting the left hand side of this equation, the force, the resultant of the forces which is acting in the x direction, equal to This term is gone because it's a steady state problem, so we are only bothered about momentum out minus momentum in. So momentum out at section 1 there is more momentum is in, not out. So momentum out in x direction is only this component, horizontal component, cos of theta component. So mv2 cos of theta component is the momentum out in x direction. And there is minus 0 means there is no momentum coming into this control volume in x direction. So I have put it 0. Similarly, I can do it for y direction. So momentum, the sum of the forces that is actually acting on the y direction would be the vertical force would be the pressure force plus the Fy force minus the W force. So these are the resultant sum of the forces that is acting in the y direction. And since this term is 0, so on the right hand side, whatever the momentum coming out in the y direction, so mv2 sin theta is the component momentum out minus the momentum coming in the y direction would be mv1. So this is how we can solve problems related with the momentum equation. So what you need is to write down your equation, and then you need to draw your force diagram as well as momentum diagram, because force diagrams help you to work out the left hand side of this equation. And if there is an accumulation, it's a steady state problem, then accumulation term in most of the cases would be 0. And on the right hand side you need a momentum flow, so you need to draw a momentum diagram so you know how much momentum going out and in. So this would be the strategy you need to solve problem, and in the next lecture we will solve problems related to that. So this is where we finishes today's lecture.